Vehicles are beginning to float, powered by nothing but invisible force. This is zero contact energy transmission, and it is quietly starting a propulsion revolution. By the end of this, you will understand exactly how this technology could make friction a forgotten relic of the past. How can a train travel at 600 kilometers per hour without touching its tracks? And what does it mean for a drone to fly forever without ever landing to recharge? What does a truly frictionless world feel like to you? Leonardo da Vinci's intricate sketches of endless motion were more than just fanciful dreams. They were an early rebellion against a universal tyrant, friction. For millennia, every turn of a wheel, no matter how brilliant, was a negotiation with this force. The wheel itself was a revolutionary idea, but it never truly escaped the grind of surface against surface. Centuries later, a new possibility emerged with the quiet hum of magnetic bearings. These devices allowed heavy industrial rotors to spin suspended in mid-air, completely contact-free. It was a profound glimpse into a new reality, yet its application remained locked away in factories. This long historical arc, from ancient dreams to magnetic levitation, reveals a simple, powerful truth. Our species has always been pushing against the limits of the physical world, seeking to move with greater freedom and less waste. That enduring quest is precisely what makes the current leap so monumental. The principles behind zero-contact energy transmission are not just an upgrade, they are a fundamental rewrite of the rules of motion. The leap from magnetic bearings to full-scale propulsion hinges on a single, elegant idea. Energy can travel through empty space. Think of the invisible fields around a magnet, a realm of pure force. This is the operating theater for zero-contact transfer. The principle is Faraday's law of induction, a cornerstone of classical physics. When a magnetic field changes near a conductor, like a coil of copper wire, it coaxes an electric current into existence without a single wire being connected. This is the same magic that lets you charge a phone by simply placing it on a pad. But for propulsion, we need more than just power, we need push. That push comes from the Lorentz force. When an electric current flows through a conductor nestled inside a magnetic field, it experiences a force, a literal shove that is perpendicular to both the current and the field. By carefully orchestrating these fields, we can generate motion, propelling a vehicle forward as if it were surfing on a wave of pure magnetism. Then there is the truly mind-bending phenomenon of quantum locking. When certain materials are cooled into a superconducting state, they can expel magnetic fields with such perfect defiance that they become locked in place, hovering and even gliding along a magnetic track without any friction whatsoever. It is a stunning demonstration of quantum physics at a human scale. These are not separate tricks but interconnected threads. The same fundamental forces that let you charge a toothbrush wirelessly are being scaled up to lift and propel high-speed trains. This is the bedrock, a fusion of classical and quantum ideas, setting the stage for the machines that are already riding these invisible rails. Magnetic levitation is no longer a laboratory experiment, it is a working reality on rails. This is the foundation of contact-free propulsion, where vehicles are lifted and pushed by pure magnetic force. Picture a train that does not roll but floats. Powerful electromagnets in the vehicle and a special guideway beneath it create a powerful repulsion. They push against each other with such consistent force that the entire mass of the train rises, hovering centimeters above the track. With the wheels gone, the primary source of friction simply vanishes, but floating is only half the battle. The train still needs to move forward. This is where linear induction motors take over. Think of them as unrolling a traditional rotary motor into a straight line. Instead of a spinning magnetic field that turns a rotor, they create a traveling magnetic wave along the guideway. This wave essentially pulls the vehicle along with it, offering seamless acceleration and deceleration without any physical contact. The result is a propulsion system of breathtaking efficiency and speed. Japan's SC Maglev train demonstrates this potential, having reached speeds exceeding 600 kilometers per hour in testing. That is faster than many small aircraft, all while gliding in near silence. The absence of grinding metal on metal also means these systems are incredibly quiet and require far less maintenance than their conventional counterparts. Magnetic levitation is the most mature proof we have that a frictionless future is not a distant dream, but an achievable reality today. Yet even this remarkable technology relies on a physical connection for its power. The next evolutionary step is to cut that final wire, unleashing true wireless energy transmission to complement this frictionless motion. Cutting that final power cable is the ultimate declaration of independence from friction. Without a constant energy supply, even the most perfectly levitating vehicle would eventually slow to a halt. This is where resonant inductive coupling enters the scene, a technology that turns the air itself into a conduit for power. You have likely experienced this with a wireless phone charger. The charger pad and your phone each contain a coil of wire. When they are tuned to the same electromagnetic frequency, they enter a state of resonance, allowing energy to leap efficiently between them across a small gap. This is not just proximity, it is a targeted, energetic handshake. For a moving vehicle, this principle can be scaled up dramatically. Imagine electrified roadways with charging coils embedded beneath the surface. As an electric car drives over them, it would receive a continuous, contactless charge, extending its range indefinitely without ever needing to plug in. But what about applications where you cannot embed coils in a road, like powering a high-altitude drone? For these longer ranges, the solution shifts from magnetic fields to focused beams of energy. Scientists are experimenting with transmitting power using highly targeted microwaves or lasers. A ground-based transmitter aims its beam at a receiver on the underside of a drone, converting the incoming energy directly into electricity to keep its propellers spinning. NASA has successfully demonstrated this with laser power beaming, using invisible light to energize small aircraft and sustain their flight for hours on end. This continuous wireless energy supply transforms the very logic of vehicle design. It means a delivery drone would no longer be limited by the weight and capacity of its battery. It could fly its entire route powered from the ground, becoming lighter, more efficient, and capable of staying aloft for as long as needed. For high-speed maglev trains, it eliminates the need for complex and heavy onboard power systems, reducing weight and boosting performance even further. The combination of frictionless movement and limitless wireless power redefines what is possible. But how do we weave these individual threads of magnetic levitation and wireless energy into a single, cohesive propulsion system that is greater than the sum of its parts? The shift from mechanical parts to invisible force fields represents the most radical redesign of propulsion in centuries. Think about a traditional jet engine, a masterpiece of engineering with thousands of spinning blades and superheated gases fighting against air resistance. Now replace all that complexity with a silent, non-moving thruster. This is the reality of ion propulsion, a field-based system already used in deep space missions. It works by ejecting a stream of charged particles, or ions, to create a gentle but continuous thrust. In the vacuum of space, where there is no air resistance, this tiny force can build up over months and years to achieve incredible speeds, far beyond what chemical rockets can provide. It is the ultimate example of precision over brute force. Back on Earth, a similar principle is at work in electromagnetic railguns. Instead of using explosive charges to launch a projectile, these systems use two parallel conductive rails and a powerful magnetic field. When an electrical current is sent through the rails, it interacts with the field to generate a massive Lorentz force, accelerating the projectile to hypersonic speeds without any combustion at all. The vehicle itself becomes the only moving part, launched silently and cleanly along its path. This fundamental redesign brings profound advantages. Systems with fewer moving parts are inherently more reliable, as there are fewer components that can wear out or break. The precision of field-based thrust allows for energy to be directed exactly where it is needed, eliminating the wasteful heat and vibration of mechanical engines. This leap in efficiency and reliability is not just an incremental improvement, it is the foundation for a new era of transportation. And the key to unlocking the full potential of these field-based systems lies in a material that seems to defy physics itself, the superconductor. Superconductors are the silent powerhouses making this frictionless vision a reality. A superconductor is a special material that, when cooled to extremely low temperatures, can carry an electric current with absolutely no resistance. This means no energy is lost as heat, a problem that plagues every ordinary wire and circuit. For magnetic levitation, this property is transformative. Superconducting electromagnets can generate immensely powerful magnetic fields without the crippling energy drain and heat buildup of conventional magnets. This makes it possible to levitate heavier loads like entire train carriages with stunning efficiency and stability. The discovery of high-temperature superconductors in the 1980s was a game-changer. While still requiring significant cooling, these materials operate at temperatures achievable with relatively inexpensive liquid nitrogen, not the far more complex and costly liquid helium. This single advance brought the economics of superconducting Maglev systems from the realm of fantasy into the sphere of serious engineering. Beyond just creating lift, superconductors are also key to dynamic propulsion. Their ability to store vast amounts of electrical energy and release it in sudden, controlled bursts enables acceleration that feels instantaneous, all without a single grinding gear. The ultimate goal, a material that superconducts at room temperature, remains the holy grail. Its discovery would instantly erase the need for complex cooling systems, making zero-contact technology as commonplace as the smartphone in your pocket. Yet, even as we push the boundaries of electromagnetism, another force of nature offers a completely different path to levitation, one that uses the power of sound itself. While superconductors push the boundaries of electromagnetism, there is another invisible force capable of lifting objects into thin air. High-frequency sound waves, completely inaudible to the human ear, can create pockets of intense pressure strong enough to defy gravity. This is acoustic levitation, a process where ultrasonic speakers generate a standing wave with precise nodes of minimum pressure. A tiny object, like a droplet of water or a piece of polystyrene, can be trapped perfectly still within one of these nodes, held aloft by the constant, pushing force of the sound itself. It looks like magic, but it is pure physics, a delicate balance of acoustic forces playing out in mid-air. The control does not stop at simple levitation. By carefully adjusting the sound waves, researchers can move these floating objects along a predetermined path, steering them through the air without a single physical touch. This makes the technology invaluable in laboratories for handling ultra-sensitive materials, from pharmaceutical compounds to biological samples. all without risk of contamination from a container or tool. Imagine a future factory where microscopic components for electronics are assembled while floating in acoustic traps, manipulated by silent, invisible sound fields. While the forces involved are currently too small to lift anything more than a few grams, the principle demonstrates a stunning alternative. Here, the medium for propulsion is not a magnetic field, but the very air we breathe turned into a precise and contactless tool. Acoustic levitation may not power our high-speed trains, but it highlights the incredible diversity of pathways we are exploring to eliminate friction. Each of these zero-contact methods, from magnetic to acoustic, promises a dramatic reduction in energy waste. But what does this collective leap in efficiency truly mean for our planet and the sustainability of our future? The silent glide of a Maglev train is more than a feat of engineering. It is a masterclass in energy conservation. Think of the roar and rumble of a conventional high-speed train, a sound that represents pure energy loss. A significant portion of its power is wasted overcoming the grinding friction of wheels on rails, energy that is instantly converted into heat, noise, and vibration. In a frictionless system, that entire category of waste simply disappears. For Maglev trains, this fundamental shift means they can operate with up to 30% less energy than their high-speed rail counterparts, even when traveling at the same incredible velocity. The energy saved is not just from eliminating rolling resistance, it also comes from a cleaner aerodynamic profile, as the vehicle is suspended without the mechanical clutter of undercarriages and bogies. The efficiency gains continue with the power source itself. Wireless energy transfer using resonant inductive coupling can achieve staggering efficiencies of over 90% across small gaps. This is not a leaky broadcast signal, but a tightly focused transfer of power where almost every bit of energy sent is received and put to work. When you combine frictionless movement with such a direct and efficient power link, the total system waste plummets. This dramatic reduction in energy demand has a direct and positive impact on our environment. Lower power consumption means fewer carbon emissions from power plants, less strain on natural resources, and a quieter, cleaner world. These systems transform speed from an energy-intensive burden into a sustainable practice. They prove that high performance and environmental responsibility are not mutually exclusive, but can be two sides of the same coin. This profound leap in efficiency, however, would be impossible without a parallel revolution happening at the molecular level, within the very materials that make these technologies possible. These leaps in efficiency are built on a foundation of advanced materials, substances engineered with almost impossible properties. At the forefront is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. It is stronger than steel, yet incredibly lightweight, and it conducts electricity better than copper. In a zero-contact vehicle, graphene composites could form the entire body shell, serving as both the structural frame and a conduit for electrical currents, eliminating the need for heavy, separate wiring. This integration of strength and function is revolutionary. Then there are carbon nanotubes, tiny cylinders of rolled graphene that possess a tensile strength hundreds of times greater than steel. Woven into cables for electromagnetic components, they can withstand the immense forces of magnetic acceleration without stretching or breaking, ensuring the system's precision and longevity. Even more astonishing are metamaterials, which are not defined by their base substance but by their intricate internal structures. These engineered architectures can bend electromagnetic waves in ways nature never intended. For wireless power beaming, a metamaterial lens could focus a microwave energy beam with pinpoint accuracy. drastically reducing spillage and boosting efficiency over long distances. Imagine a laser-like power transmission that never wavers, even to a vehicle moving at extreme speeds. Another fascinating development involves shape memory alloys. These metals can be deformed but will snap back to their original shape when heated, acting like artificial muscles. In a frictionless craft, panels made from such an alloy could subtly change their form in response to temperature changes from air friction, continuously optimizing the vehicle's aerodynamics for minimum drag throughout its journey. These materials collectively enable designs that are thinner, lighter, and far more durable. They transform theoretical possibilities into practical engineering, allowing us to build structures that can handle the intense, non-contact forces at play. The right material does not just make the technology better, it makes it possible at all. And as these physical systems grow more complex, managing their immense data and precise control requires a new kind of intelligence, one that operates at the speed of light. Managing thousands of magnetic fields and power beams in real time is a task far too complex for any human operator. This is where artificial intelligence steps in, acting as the central nervous system for these frictionless machines. An AI can process a constant flood of data from hundreds of sensors, instantly calculating the precise adjustments needed to keep a Maglev train perfectly levitated or a drone steadily locked onto a power beam. It is a dynamic dance of force and feedback, all happening in milliseconds. This real-time control is not just about maintaining stability, it is about optimizing for peak efficiency, ensuring not a single joule of energy is wasted. Beyond immediate control, machine learning algorithms pore over this operational data, searching for subtle patterns that hint at future problems. They can detect a minute change in the vibration signature of a linear motor or a tiny dip in the efficiency of a superconducting coil, predicting a maintenance need long before a critical failure occurs. This shift from scheduled repairs to predictive maintenance means systems can fix themselves before they break, achieving a new level of reliability and safety. The intelligence even extends to the very shape of the vehicles themselves. Using a process called computational fluid dynamics, AI can simulate millions of slightly different vehicle designs, testing them in a virtual wind tunnel to find the form that slices through the air with the absolute minimum of drag. The resulting shapes are often beautifully organic, curves and contours born not from an artist's sketch but from pure data-driven optimization. This relentless pursuit of efficiency continues into the energy network itself. In a city where multiple vehicles are drawing wireless power simultaneously, an AI dispatcher acts as a master conductor. It dynamically balances the distribution of energy, ensuring a steady, stable supply to every receiver without overloading the grid. It might momentarily boost power to a train accelerating up a grade while slightly reducing the beam to a drone cruising steadily overhead, all in a seamless, invisible orchestration. This deep integration of smart software is the final piece that makes autonomous frictionless transport not just possible, but practical. A self-piloting vehicle that never touches anything and draws power from the air requires a governing intelligence to tie it all together. But to weave these intelligent, zero-contact systems into the fabric of our daily lives, we must first reimagine the world they will operate within. Building this new world of movement demands a new kind of skeleton for our cities and landscapes. Widespread adoption of zero-contact propulsion means constructing electrified guideways where Maglev trains can glide and deploying networks of power beaming stations that act as invisible fueling stops for the sky. These are not minor additions to our existing infrastructure. They are the foundation of an entirely new transportation layer. The energy demand for such a system is immense, requiring a robust and intelligent electrical grid. To power a continent of floating trains and perpetually flying drones, we would likely need to integrate vast fields of solar panels and wind turbines directly into the grid, transforming the energy source to match the clean efficiency of the vehicles themselves. Within cities, the challenge shifts to space and integration. Elevated guideways could arc between skyscrapers, or routes might dive underground to preserve precious surface land, demanding a fresh approach to urban planning that weaves these new pathways into the existing urban fabric without causing massive disruption. Perhaps the most crucial and often overlooked requirement is standardization. A Maglev train from one country must be able to glide seamlessly onto the guideway of another. A delivery drone must understand the power beaming protocol of every city it enters. This demands a universal language of magnetic fields, communication signals, and energy transfer, agreed upon by nations and corporations alike. The initial investment for such a comprehensive overhaul is undeniably vast, involving not just new materials but a complete rethinking of our logistical backbone. Yet the long-term payoff in unparalleled speed, radical energy efficiency, and silent, clean transportation could redefine global connectivity. We are already seeing the first blueprints of this future take shape in pioneering projects around the globe. The proof is already gliding across the landscape of East Asia. Japan's SC Maglev train is not just a prototype, it is a record holder, having carried passengers at 603 kilometers per hour. This astonishing speed is achieved through the silent, relentless push of superconducting magnets, lifting the train so that its only real opponent is the air itself. For over 2 decades, this technology has been refined on a dedicated test track, a sustained experiment pushing the very definition of ground travel. Meanwhile, in China, the Shanghai Maglev train offers a different kind of proof, that of daily utility. Since 2004, it has shuttled commuters and travelers between the city and its airport, covering 30 kilometers in a mere 7 minutes. This is not a test, but a working public service, demonstrating that frictionless transit can be a reliable part of urban life. The passenger experience in these vehicles is fundamentally different. The roar of steel wheels is replaced by the quiet hum of electromagnetics and the whisper of air resistance. The ride is so smooth that a standing passenger feels no need to brace themselves, a sensation more akin to flying than to traditional rail. This operational elegance translates directly into economic benefits. With no physical contact between the train and the guideway, the wear and tear that plagues conventional railways is almost entirely eliminated. The long-term maintenance costs are dramatically lower because there are simply far fewer moving parts to break or replace. These two systems, one a high-speed pioneer and the other a commercial workhorse, provide undeniable evidence. Zero-contact propulsion is no longer a futuristic concept. It is a viable, tested solution for high-speed ground transportation. Their success has ignited a global spark, with nations across Europe and the Middle East now planning their own Maglev corridors. The lessons learned from these steel rails are ready for translation, ready to be applied to vehicles that leave the ground behind entirely. What happens when we take this principle of frictionless, contact-free propulsion and point it toward the sky? Aerial drones could soon operate as permanent fixtures in the sky, their batteries continuously replenished by an invisible laser fired from the ground. This transforms their role from short-range couriers to persistent aerial platforms, capable of monitoring traffic, delivering emergency supplies, or providing communication links for days or even weeks without interruption. The drone itself becomes a simpler, lighter machine, its design unburdened by the need to carry massive amounts of onboard power. but the principle of contactless thrust finds its ultimate expression far above our atmosphere. In the void of space, ion thrusters have already become the workhorses of deep space exploration. These devices use electric fields to accelerate charged particles, or ions, to tremendous speeds, ejecting them from the spacecraft to generate a gentle, continuous push. The force is so faint it could not lift a piece of paper on Earth, but in the frictionless environment of space, that tiny thrust accumulates. Over months and years, it can accelerate a probe to velocities far beyond the reach of traditional chemical rockets, all while using a fraction of the fuel. This incredible efficiency is what allows missions to journey to asteroids and the outer planets, operating for decades on a single tank of propellant. Looking even further ahead, concepts like the space elevator envision a cable stretching from Earth's surface into geostationary orbit. Magnetic levitation cars climbing this tether could lift payloads into space using nothing but electrical power, rendering the violent, explosive nature of rocket launches obsolete. The cost of accessing orbit would plummet, opening the heavens to routine commerce and construction. This is the true power of zero-contact systems, their adaptability from the crowded urban canyons of our cities to the limitless expanse of the cosmos. They offer a unified physics for movement, whether through air, across land, or in the vacuum of space. But what does it cost to build this new world, and who will pay for it? The price tag for a frictionless future is undeniably steep. Building magnetic guideways and power beaming stations requires immense upfront investment, far beyond that of conventional steel rails and roads. The specialized materials, from high-temperature superconductors to carbon nanotube composites, are still expensive to produce at scale, yet this initial cost tells only half the story. The true economic picture emerges over decades of operation. A Maglev guideway, once built, has virtually no wear from contact, eliminating the relentless, costly cycle of grinding down and replacing wheels and tracks. The energy savings compound year after year, with frictionless vehicles consuming significantly less power to achieve higher speeds. When you run the numbers, the long-term operational cost per kilometer for a mature Maglev system can actually fall below that of traditional high-speed rail, turning a capital-intensive project into a financially sound investment over its lifetime. This economic shift would ripple far beyond the transportation sector. An entire new industry could blossom around wireless energy transmission. Imagine factories dedicated to manufacturing the intricate coils for resonant charging roadways, or specialized crews trained to maintain and calibrate networks of laser power beaming stations. This represents a new frontier for engineering, construction, and technical services, creating high-skilled jobs that do not even exist today. The challenge, of course, is ensuring this new world of motion does not become a luxury available only to the wealthy. The high cost of initial infrastructure could widen existing mobility gaps if left solely to market forces. This is where innovative funding models become critical. Public-private partnerships could share the financial burden, using government backing to de-risk the project for private companies, with the ultimate goal of making the service affordable for everyone. A thorough cost-benefit analysis must look beyond simple balance sheets. How do you quantify the economic value of a silent city, free from the rumble of trains and the roar of engines? What is the worth of time saved when commutes are cut in half, or of cleaner air from drastically reduced emissions? The gains in efficiency and the spark of new innovation could reshape regional economies, connecting cities into powerful, integrated megaregions where distance is no longer a barrier to commerce. The transition is a monumental financial undertaking, but the potential returns, a faster, cleaner, and more connected society, are equally vast. Yet, for all this economic potential to be realized, the public must have absolute confidence in the system. What happens when a vehicle traveling at 600 kilometers per hour loses power, or when a magnetic field fails? The promise of economic gain rests entirely on a foundation of flawless safety and unwavering reliability. A vehicle suspended by invisible fields cannot simply swerve or skid. It can only follow the precise path dictated by its magnetic guideway. This inherent stability eliminates some of the most common and catastrophic failures in traditional transport, like derailments at high speed or catastrophic tire blowouts. The absence of physical contact means there is no surface to wear out suddenly and cause a loss of control. Yet, this new paradigm introduces its own unique set of vulnerabilities. A momentary power fluctuation or a stray signal causing electromagnetic interference could disrupt the delicate balance of forces holding the vehicle aloft. A misaligned power beam intended to wirelessly energize a drone could miss its target by a fraction of a degree, leading to an unexpected loss of thrust. The entire system operates on a foundation of perfect real-time coordination, and any break in that chain presents a risk. To counter these new dangers, engineers build in layers of redundancy. Multiple, independent sensor arrays constantly monitor the vehicle's position, the strength of the magnetic fields, and the integrity of the power link. If one sensor fails, two others are already confirming the data. This network feeds into fail-safe mechanisms designed for graceful recovery, not catastrophic failure. Should a primary system falter, backup electromagnets can engage within milliseconds to maintain levitation, or an onboard energy storage unit, like a supercapacitor, can provide enough power for a controlled, safe stop rather than an abrupt fall. This constant, automated vigilance extends to the digital realm. The complex artificial intelligence controlling these systems represents a potential target for cyber attacks. A malicious actor gaining control of a Maglev network's operating software could theoretically orchestrate chaos. This makes cybersecurity a core component of the safety design, not an afterthought. Control systems are isolated within fortified digital fortresses, with multiple encryption layers and continuous intrusion detection scanning for any anomalous activity. The goal is to make the system not just physically resilient, but digitally impregnable. For the public to truly embrace this technology, they need to see proof that it is as safe or safer than the trains and planes they already trust. This demands a new culture of radical transparency and testing. Prototypes undergo millions of kilometers of simulated and real-world trials, deliberately forcing failures to see how the system responds. Data from every sensor reading, every power fluctuation, and every software command is logged and analyzed, building an unimaginably detailed record of performance. This evidence is what builds the essential, intangible foundation for a frictionless future: public trust. With that trust secured through demonstrable safety, we can fully appreciate the profound environmental payoff of a world that has moved beyond friction. The silence of a frictionless city is its first and most profound gift. Without the constant grind of wheels on pavement or the shriek of steel on steel, the urban soundscape transforms. The dominant noise becomes the soft rush of wind, a gentle backdrop that allows for conversation, for thought, for a calmer human experience. This dramatic reduction in noise pollution is a direct result of eliminating mechanical friction, the primary source of the roar we associate with transportation. But the benefits reach far deeper than just quiet. The lower energy consumption of these systems is a direct assault on greenhouse gas emissions. A Maglev train, for instance, uses significantly less electricity to achieve the same speed as a conventional high-speed train. When that electricity is sourced from renewables like solar or wind farms, the entire chain of movement becomes virtually carbon neutral. This is not a marginal improvement. It is a fundamental shift toward decoupling our mobility from the burning of fossil fuels. The environmental care extends to the materials themselves. Think of the countless liters of oil, grease, and hydraulic fluid that keep traditional vehicles running, substances that inevitably leak and run off into soil and waterways. A zero-contact system has no gears to grind, no axles to grease. The absence of these consumables means a drastic reduction in chemical pollutants, protecting local ecosystems from this slow, steady contamination. Perhaps the most systemic benefit lies in efficiency. When individual vehicles can move faster and with greater capacity, we may need fewer of them overall. A single, perpetually flying drone could replace a fleet of ground-based delivery vans stuck in traffic. This consolidation reduces not just congestion, but the total material and energy footprint of our entire transportation network. The sustainability of this technology is not a happy side effect. It is a core design feature, positioning it as a central pillar of a truly green industrial future. Yet for all this promise, the path to a frictionless world is not without its own significant hurdles and necessary trade-offs. Even the most elegant technology must contend with the stubborn realities of physics and economics. Wireless power transmission faces a fundamental trade-off between range and efficiency. As the distance between a transmitter and receiver grows, the energy beam naturally spreads out, losing its intensity and leading to significant power loss over longer distances. For a drone relying on a ground-based laser, flying too high means the signal becomes too weak to provide meaningful thrust. The solution is not a single magic bullet, but a network of intelligent relay stations. Picture a series of towers positioned between cities, each one catching a power beam, amplifying it, and retransmitting it to the next station, creating a continuous energy highway through the sky. This approach maintains high efficiency over vast distances, but it requires building an entirely new infrastructure layer. The materials themselves present another major hurdle. While high-temperature superconductors are a massive improvement, they still require constant and costly cooling with liquid nitrogen. The sheer expense of manufacturing these specialized materials and maintaining their fragile cryogenic environments currently limits their use to large-scale, well-funded projects. For zero-contact propulsion to become as common as the family car, we need a breakthrough in materials science, perhaps a composite that can mimic superconducting properties at more manageable temperatures. Then there is the challenge of scale. A laboratory prototype levitating a small model is one thing. Engineering a full-size passenger vehicle that does the same is a monumental leap. The magnetic fields must be immensely stronger, the control systems infinitely more precise, and the structural integrity of the entire guideway must handle forces far greater than anything in a test environment. Every component must be scaled up in perfect harmony, a symphony of engineering where one miscalculation can disrupt the entire system. Beyond the technical puzzles lies the human dimension. Public skepticism about the safety of riding on invisible force fields or concerns about the health effects of pervasive energy beams can slow adoption as much as any engineering flaw. Regulatory bodies accustomed to certifying vehicles with wheels and wings must develop entirely new safety standards for a technology that operates on completely different principles. Overcoming these barriers demands more than just better hardware. It requires a concerted effort in public education and transparent demonstration projects that build trust through first-hand experience. These are significant obstacles, yet none are insurmountable. They simply define the work that lies ahead, a global research endeavor pulling from physics, materials science, and social engineering. The steady progress in labs around the world suggests that solutions are, indeed, on the horizon. But navigating this complex transition from prototype to public utility cannot be left to scientists and engineers alone. It demands a framework of support and guidance that only coordinated government policy can provide. The invisible architecture of policy is what will turn these engineering marvels into public utilities. Governments hold a unique power to accelerate this transition, not by building the vehicles themselves, but by creating the fertile ground where innovation can take root and flourish. Consider the precedent set by the global push for renewable energy. Decades of targeted government funding for solar and wind research transformed niche technologies into mainstream power sources, driving down costs through sustained investment. A similar commitment to zero-contact propulsion, with public grants for fundamental research into new superconductors or more efficient power beaming, could shave years off the development timeline, bringing the future of travel that much closer. But funding alone is not enough. The public's trust must be earned and protected through clear, intelligent regulation. We need new safety standards that address the unique realities of this technology. What are the safe limits for long-term human exposure to the powerful electromagnetic fields that levitate a train? How do we certify the cybersecurity of an AI that controls thousands of vehicles simultaneously? Proactive regulators must answer these questions long before the first public systems are launched, ensuring safety is baked into the design from the very beginning. For private companies, the initial financial risk of building magnetic guideways or power beaming networks is enormous. This is where strategic government incentives become a powerful catalyst. Tax credits for constructing zero-contact infrastructure or grants for retrofitting existing transit corridors could unlock billions in private capital. These policies effectively share the risk, making it economically viable for businesses to invest in building the skeleton of this new world. The ultimate goal, however, is a seamlessly connected planet. A maglev train cannot stop at a national border because its magnetic guideway is incompatible with the next country's system. This demands a level of international cooperation rarely seen outside of diplomacy. Nations must come together to create universal technical standards for everything from the frequency of wireless power transmission to the communication protocols between vehicles and guideways. Imagine a global treaty for frictionless travel, ensuring a drone or a train designed in one nation can operate flawlessly in any other. This harmonization is the key to unlocking truly global, high-speed networks. The role of policy, then, is to be the great enabler. It provides the funding for the initial leap, the regulations for safe landings, the incentives for private enterprise to build, and the diplomatic framework for a connected world. With this supportive architecture in place, the pace of change will not be incremental, it will be transformational. This foundation of global policy sets the stage for a future that is now rushing toward us, a horizon shaped by trends we are only beginning to perceive. A Hyperloop pod does not fight the air, it evades it entirely. Sealed within a tube where most of the atmosphere has been removed, the last great source of friction simply vanishes. Inside this near-vacuum tunnel, a capsule levitated by magnets faces almost no resistance, allowing it to coast for miles on a fraction of the energy a high-speed train would consume. Propelled by linear motors, these pods could theoretically surpass 1,000 kilometers per hour, making a cross-country trip feel like a commute across town. This is not just a faster train, it is a fundamentally different environment for motion, a sealed highway where speed is limited only by our ability to maintain the vacuum and control the magnetic forces within. Beyond the familiar physics of magnets and vacuums lies a frontier that seems pulled from science fiction, the potential of quantum entanglement. In this bizarre quantum phenomenon, two particles can become linked or entangled so that a change to one instantly affects the other, no matter the distance separating them. While we are far from entangling objects you can see, researchers are exploring if this spooky connection could one day be harnessed to transmit energy or information across vast interstellar spaces. Imagine a deep space probe light years from Earth receiving power instantly from a solar station back home through a quantum link. This would be the ultimate form of wireless energy, a connection that transcends distance and travel time. Closer to home, these vehicles will not operate in isolation. They will be living components of a smart city's nervous system. An autonomous Maglev pod would communicate directly with the traffic control AI, receiving real-time updates to adjust its speed and spacing for perfect flow. It would seamlessly integrate with other zero-contact systems, perhaps gliding from a main transit tube directly into the magnetic parking bay of your office building, all while wirelessly settling its electricity bill with the municipal grid. This deep integration turns isolated trips into a single, continuous journey. This logic of seamless, intelligent mobility could eventually scale down to the personal level. The hoverboard of popular culture may one day become a reality, not as a magical device, but as a compact platform using acoustic levitation or localized magnetic repulsion to float just above a specially treated pathway. Personal flying vehicles, long a staple of futuristic dreams, could utilize distributed electric propulsion with dozens of tiny, quiet fans, their navigation managed by the same city-wide AI that guides the larger transport pods. The boundary between public transit and personal mobility would begin to blur. These converging trends sketch a future where zero-contact propulsion is not a novelty, but the default, the invisible backbone of a society in motion. Yet this very integration forces us to confront profound ethical questions. Who has access to this frictionless world, and who is left behind on the old, crumbling roads? How do we protect the privacy of citizens when every movement is tracked by the infrastructure that enables it? The technology promises unparalleled freedom, but it is our collective wisdom that will determine whether that freedom is shared by all. A frictionless world must be a fair one. The first train to glide on magnetic fields will likely connect two wealthy financial districts, not a remote rural community. This initial deployment pattern risks creating a stark divide, a two-tiered society where speed and efficiency are luxuries for the affluent, while others remain stuck in the congestion of the past. Equitable distribution is not a secondary concern, it is a core engineering challenge. We must design these networks with the explicit goal of serving underserved areas, perhaps by integrating zero-contact bus routes into existing public transit to bridge the gap, ensuring the benefits of this new mobility reach everyone, not just a select few. This technological shift will inevitably reshape the workforce. What happens to the millions of truck drivers, railway maintenance crews, and logistics managers whose jobs are built around the friction-filled systems of today? Their expertise is invaluable, but their roles will transform. A proactive approach demands large-scale retraining programs funded by both industry and government to transition these workers into the new jobs this revolution will create. They could become specialists in maintaining magnetic guideways, operators for the AI control systems, or technicians for wireless power networks. This is not about replacing people, but about reinvesting in human potential. Then there is the silent cost of convenience, the erosion of privacy. A smart infrastructure that tracks every vehicle's position and energy consumption in real time is also, by its very nature, a pervasive surveillance system. The same data used to optimize traffic flow could be misused to monitor the movements of citizens. Without robust, forward-thinking data protection laws, The freedom of frictionless movement could come at the price of constant observation. Ethical design must therefore be a non-negotiable principle, embedding privacy safeguards directly into the architecture of these systems, ensuring that data is anonymized and used solely for its intended purpose of safe and efficient operation. The ultimate goal is to enhance human well-being, not just to achieve a technological marvel. This means considering the psychological impact of living in a world of silent, invisible vehicles, and designing urban spaces that feel human-centered, not machine-dominated. It requires asking difficult questions before the first foundation is poured. Who benefits, who is at risk, and how do we steer this powerful technology toward a future that uplifts all of society? By confronting these ethical dilemmas head-on, we build not just a more efficient world, but a more just and trustworthy one. The solutions to these profound challenges are being forged in laboratories and research centers around the globe, where the next generation of breakthroughs is already taking shape. Laboratories around the world are buzzing with quiet revolutions. One of the most urgent focuses is on stretching the reach of wireless power, pushing it beyond short-range charging pads. Researchers are experimenting with a technique called resonant beam charging, where a laser or microwave beam is precisely tuned to resonate with a receiver. This creates a stable, efficient energy link over distances of hundreds of meters, a potential game-changer for keeping high-altitude drones or even low-orbiting satellites powered from the ground. This is not a scattered broadcast, but a tightly focused energy thread, like a perfectly aimed spotlight of pure power. In parallel, the quest for the holy grail of material science continues unabated, the room-temperature superconductor. Teams are testing new combinations of hydrogen-rich compounds under immense pressure, or exploring layered quantum materials that show flickers of zero resistance at temperatures once thought impossible. A successful discovery here would instantly shatter the biggest barrier to widespread adoption, eliminating the complex and expensive cryogenic cooling systems. Zero-contact technology would leap from specialized infrastructure to everyday consumer products, as manageable as the electronics in your home. The ripple effects of this research are already surfacing in unexpected fields, most notably in medicine. Biomedical engineers are developing tiny, implantable devices like pacemakers and neural sensors that can be powered and recharged entirely through resonant inductive coupling from outside the body. This eliminates the need for risky replacement surgeries to change a battery, offering patients a new level of freedom and safety. It is a powerful demonstration that the principles of contactless energy transfer are not confined to transportation, but are a universal tool with cross-disciplinary potential. These breakthroughs are rarely born in isolation. They are fueled by unprecedented collaborations, where university theorists share data with corporate engineering teams, and government grants fund the high-risk, high-reward research that private companies might avoid. Open-source hardware and software projects are accelerating innovation, allowing hobbyists and startups to build upon the latest findings without prohibitive costs. This collective, global brain trust is what makes the current pace of discovery so electrifying. For anyone watching this space, staying informed is no longer a passive activity. It is an essential part of understanding the future taking shape. This rapid evolution naturally opens a door for participation. How can a visionary company or an individual engineer get involved in building this frictionless world? Your career could be the very catalyst that brings this frictionless world to life. For entrepreneurs, the landscape is rich with uncharted territory, from startups designing next-generation wireless charging coils to firms specializing in the advanced composites needed for Maglev guideways. These are not just niche markets, they are the foundational industries of a new era, offering the chance to build a business that literally shapes the future of how humanity moves. The path for students is equally direct, focusing their studies on the core disciplines that underpin this revolution. Degrees in electromagnetics, sustainable engineering, or materials science provide the essential toolkit, transforming abstract curiosity into the practical ability to manipulate force fields and engineer matter itself. This is where theoretical knowledge becomes the power to build. You do not need a corporate lab to start experimenting. Hobbyists are already pushing boundaries with astonishingly accessible projects. A simple acoustic levitator can be built with off-the-shelf components, allowing you to float small objects using sound waves right on your workbench. Constructing a miniature Maglev model teaches the hands-on principles of magnetic repulsion and stability. These small-scale experiments are more than just fascinating demonstrations. They are the first steps in a learning journey that could lead to a major breakthrough. For those whose passion lies in advocacy, supporting organizations that lobby for clean transportation infrastructure is a powerful lever for change. By helping to shape public policy and secure government funding, you can accelerate the adoption of these technologies on a societal scale, ensuring the frictionless future is prioritized on the political agenda. Every contribution, whether a career choice, a personal project, or a voice for change, adds a critical thread to the larger tapestry. This collective and diverse involvement is what transforms a technological possibility into an inevitable reality. As these individual efforts multiply, they feed into a much larger dynamic, a complex global dance of competition and cooperation that is setting the course for our collective future. National pride and economic ambition are fueling a global race to master this frictionless future. Japan's decades-long investment in the SC Maglev is a statement of technological sovereignty, while China's expanding network of urban Maglev lines demonstrates its capacity for rapid, large-scale implementation. Across the Pacific, the United States is channeling significant resources into its own Hyperloop and wireless power beaming initiatives, viewing the technology as a new frontier for both transportation and national security. This intense competition creates a powerful engine for innovation, with each breakthrough in one nation pushing rivals to achieve more, driving down costs and accelerating development timelines for everyone. Yet, the most ambitious visions cannot be contained by borders alone. The proposed Europe-Asia Maglev network presents a staggering engineering challenge, a ribbon of magnetic guideway stretching across continents, through mountain ranges and over vast plains. Such a project demands more than just funding. It requires a shared technical language and a diplomatic framework to reconcile differing safety standards and operational protocols. It is here that collaboration becomes the critical enabler. Organizations like the International Union of Railways provide a neutral ground where engineers and policymakers from competing nations can agree on universal specifications. They work to standardize everything from the voltage of inductive power rails to the communication signals that prevent vehicles from different manufacturers from interfering with one another. This harmonization is not just about convenience, it is what makes large-scale, interoperable systems financially viable, preventing a future of isolated, incompatible networks. This intricate dance of rivalry and partnership defines the current era. Competition sparks the initial leaps, while cooperation ensures those leaps can be connected into a cohesive global system. The result is a rising tide that lifts all boats, where a material breakthrough in an American lab can improve the efficiency of a German Maglev prototype, which in turn influences the design of a station in Saudi Arabia. This dynamic global landscape is not a side note, it is the very ecosystem in which this technological revolution is growing. As these international networks begin to take physical form, They promise to reshape more than just our maps. They are poised to fundamentally alter the rhythm of our daily lives and the structure of our societies. The very definition of a city could transform around this silent, swift movement. With commute times slashed from hours to minutes, the gravitational pull of a downtown office weakens. You could choose a home for its mountain view or its coastal air, not its proximity to a train station, because the distance itself becomes almost irrelevant. This liberation from the clock rebalances our lives, trading stressful hours in traffic for time with family, for hobbies, or simply for rest. Urban planners would seize this opportunity to reimagine city cores. Vast parking lots and congested multi-lane roads, relics of a friction-filled past, could be reclaimed. In their place, we might see parks, community gardens, and pedestrian promenades flourish. The city's skeleton would be redrawn around compact, hyper-efficient transit hubs where Maglev pods arrive and depart in a silent, continuous ballet. This shift away from car-centric sprawl encourages denser, more walkable neighborhoods, fundamentally altering the rhythm and feel of daily life. This new mobility logic also challenges our deep-seated idea of ownership. Why own a car that sits idle 95% of the time when a shared, autonomous pod could be summoned on demand? A subscription to a mobility service would grant you access to a vehicle for any need, from a solo commute to a family trip, without the burdens of insurance, maintenance, or parking. This model dramatically lowers the cost of transportation for the individual while reducing the total number of vehicles required, saving immense resources in manufacturing and raw materials. The cumulative effect is a profound enhancement of human well-being. The constant, low-grade stress of a bumper-to-bumper crawl is replaced by the calm, productive glide of a frictionless journey. The environmental payoff is just as significant, with cleaner air and quieter streets contributing directly to public health. Adapting to this new reality requires a societal pivot, embracing flexibility over fixed routines and shared access over private possession. It is a cultural evolution as much as a technological one. This long-term vision points toward a world where movement is so effortless, so seamlessly integrated into the background, that it finally ceases to be a burden and becomes a pure facilitator of human potential. That distant vision is a world seamlessly stitched together by silent, swift currents of motion. Entire continents could be linked by high-speed magnetic arteries, where a journey from one coast to another becomes as simple and routine as a cross-town bus ride is today. Global travel would shed its complexity, transforming into a smooth, continuous flow that makes distant cultures and economies immediate neighbors. This connectivity extends beyond the vehicles themselves to the very energy that powers them. Vast solar farms in sun-drenched deserts and wind installations in remote plains could beam their harvested energy wirelessly across thousands of kilometers, creating a global power grid that directly fuels both our homes and the transit networks that connect them. In such a world, friction becomes the exception, an almost forgotten inconvenience rather than the daily norm that dictates design and drains efficiency from every action. This level of integration is the ultimate expression of the principles we have traced, from the first floating magnetic bearing to the quantum entangled power links of tomorrow. Achieving it is an ambition of staggering scale. Yet every new Maglev line that enters service and every efficiency record broken by an ion thruster is an incremental step that makes this future more tangible. Embracing this path demands sustained optimism and a collective commitment to effort, but the potential rewards are a civilization liberated from the drag of its own machinery, operating with a quiet, effortless grace. Our journey has taken us from Leonardo da Vinci's sketches to the silent glide of trains that float on force fields. through the invisible power beams that keep drones aloft and the smart materials that make it all possible. We have seen how this technology redefines efficiency, reshapes cities, and even alters the economics of movement itself. The frictionless future is no longer a dream, but a direction. The call to action is not for everyone to become an engineer, but for all of us to become informed advocates, curious learners, and supportive voices for the clean, efficient, and profoundly human-centered world that this technology promises to build. The choice to move forward, after all, is the one that has always defined our progress. Our journey from floating trains to wirelessly powered drones reveals a world where motion is no longer a fight against friction. The core promise of this technology is a cascade of benefits, starting with radical efficiency. By eliminating the grinding waste of physical contact, these systems operate with a silent elegance that saves immense amounts of energy, transforming speed from an expensive luxury into a sustainable standard. This leap in performance is inextricably linked to a cleaner environment, where silent vehicles glide through cities free from the exhaust and particulate pollution of their predecessors. Yet this bright future cannot be built by engineers alone. It requires a foundation of supportive policies, international cooperation, and a massive investment in new infrastructure, from magnetic guideways to power beaming networks. The ultimate transformation is one of experience. Transportation becomes faster, yes, but also profoundly more reliable and accessible, weaving distant communities into a single, interconnected fabric. We are standing at the edge of this new era, watching the first prototypes become working realities. Your perspective is a vital part of this evolution. What excites you most about a frictionless world, or what concerns do you hold? Share your voice in the comments below. And if you want to continue exploring the frontiers of tomorrow, subscribe for more. The path to a smoother, smarter world is one we build together, one idea and one conversation at a time.